Okay, one more reminder, page 252, section 5.3, this is called graphing radical functions. And really, we're only gonna graph two radical functions. Well, two radical functions and circles. That'll be fun. Two radical functions and circles. Y'all there? Page 252? Okay. You all know, I think, what the graph of this looks like. We put it up here many times, yeah? Okay, well this is the graph of quadratic function. What we're gonna be graphing today is like unto it, but it's gonna be opening in a different direction. It looks like this. It's the inverse of that, which is the square root of x. That's one of the things we're gonna be doing. I don't know for sure if you have a really good idea in your mind what this looks like, do you?
Those in 3 points.
We'll take a look at what it looks like, but we're also going to graph its inverse. We're going to graph those two things, focus on how we handle those, and then we are also going to graph circles, which I'll talk about in a few minutes. Let's take a look at what these parent functions look like. And I'm talking about, I'm just asking you to compare those because you know what these look like. These look like it too, only they're inverse of each other. And if you'll remember, inverses, I don't know if you remember learning this or not, but inverses reflect over the line y equals x. Have you ever heard that? Or no? Have I? No? Okay. Anyway, if I were to plug, well, I'll just get some points out here so that we can see that there are points on it that link together to make the, if I choose, for example, -2 and -1 and 0 and 1, 2 and 3 and 4 for x's. First of all, notice that if I plug -2 in, I got nothing. You can't square root a negative, right? If you plug -1 in, can't do it. If you plug -0.5 in or -0.01 in, you cannot do it. The first point that's a viable point on this thing is 0. And the square root of 0 is 0. Square root of 1 is 1. Square root of 2, that's a poor choice because I don't want to square root 2. It's irrational, so I'm going to choose some other things over here. Let's choose, what's the next thing I can square root evenly? 4, and that would be 2. And the next thing? 9, and that would be 3. So if you choose your x's, since it's up to you when we graph these things like this, you can choose what you want so that things come out whole. And I can't graph anything over here. So what that means, folks, is when you see this, the domain of this function is from 0 to the right. There's nothing to the left. Okay, so that's the first thing to note. The domain of this function is those x values which are greater than or equal to 0. Nothing negative works. Okay, so I'm going to graph these. I'm going to turn this way. I hope it's not too distorted. Okay, so if I graph those points right there, the ones that work, I get 0, 0, 1, 1, 4, 1, 2, 3, 4, 2, and 4, 5, 6, 7, 8, 9, 3. So this is what those things look like. And that kind of looks like a parabola that's opening out to the right, right? Except you only get the top half. Because, listen carefully, this is going to be the explanation. This is the reason why when you square root with this crazy radical symbol on it, that you're only allowed to do the positive ones. The positive ones that work. Remember that when you have that funny little symbol on there, it means find the principal square root of whatever you're plugging in, which means only these positive numbers here, not the negatives that go with them, just the positives. Why? Because if I had the negatives, this thing would come down here, and we would have a non-function. Fails the vertical line test if you have this branch down here, right? You follow me there? Mm-hmm. And this is called a radical function. And so we restrict it to only principal square roots so that what does get graphed is a function. You with me there? So that's your explanation as to why that is. And it may not be very satisfying, but that's the explanation, okay? All right, now let's take a look at this function right here. I'll graph it in a different color. Well, maybe I'll just erase the other one because it's kind of hard when you get a whole bunch of junk up there on the graph. So, oh good, you can still see this, okay. X and Y on this one. If I choose, let's say, -8 and -1 and 0 and 1 and 8, why am I doing that? Just easy to keep readable, right? Can I plug a -8 in there?
Yes.
Yes, you
It's
can.
two, negative
And it's -2. Remember, you can cube root negatives and you get a negative for it. You with me there? What's this one? -1, 0, 1, and 2. Okay. So the y values don't get big very fast. The x values get big really fast. If we want to find whole ones to plot. So I'll do this one over here. We'll do this in yellow. It's a -8, -2. So I gotta go back and down 2, and then only back 1, and whoops, and down 1, and then a 0, and then a 1. That almost looks linear, except for it's going to connect way out here. We got 1, 2, 3, 4, 5, 6, 7, 8, and up 2. And so this bends it pretty harshly coming in this way, and it flattens out. It doesn't flatten out on the 2. I mean, by the time you get out here to -27, it has dropped down to 3, but it's a very shallow drop. So it's coming across like this, and it's going to stay in that region for quite a while. You with me there?
Yeah.
Okay. And we go up here and we try to hit this, and then we cross it. We cross it, and it goes up like this really slowly until we get out to 27, where it'll hit 3. It's not a very exciting graph, and neither was the other one. I realize that. But the exciting thing, if you like excitement, is happens right here. Okay, now, you got an idea what these two things look like?
Yep.
If you forget what they look like, they are in the core concept at the top of page 252. Both of them are graphed right there for you. You can remember what they look like. Okay, what we are going to do, as we seem to always do with new parent functions, is transform them. Do you remember your transformations, or do you want me to write them down? Maybe as we hit them, if you can't remember how to do a particular transformation, I can explain it then. I can save a lot of time if we don't have to go through the transformations again. If you forget some of the details, that is in the core concept at the top of page 253. Transformations, the notation that you use, and examples of what would happen if you used them. There's 6 of them. Do you remember? Okay, I'm not going to go through it then. We are going to go down to example 1. I know that they gave that core concept after example 1, but on example 1, what they're actually doing is plotting points, and I don't want to do that. If you remember your transformations very well, I'm going to do example 1 using transformations rather than plotting points. I am done plotting points. Okay? All right, so in example 1, we are supposed to graph the A part. F of x equals the square root of 1/4 x. What sort of transformation is that on the parent function?
horizontal stretch by 4.
Horizontal stretch of 4 means we're going to take the square root function, which isn't up there. Remember, the square root function looks like this, just in a general way. It looks like this. And we're going to grab the ends of it, or maybe hold this end right here. We're going to take this one, and we're going to horizontally stretch it 4, which means it's going to get flatter, a lot flatter, right? It's going to look something like this. And it's not going to grow very fast, because this is what we're going to do, folks. We're going to take 1/4 of whatever we put in here and then square root it. So to get the first whole thing, I'm going to have to put a 4 in here, where it used to be just a 1. You see what I'm saying?
Yeah.
Okay, and the next square rootable thing after 1 is 4. I'm gonna have to put a 16 in here to get a 4 to square root, which would be 2. You following me there? Okay, so this thing's going to be a lot flatter. It's going to, and you might want to put a couple of points in there just to see where it's going to intersect, but it's going to be flatter like this. And notice what they do on the example. You need to notice this, because that thing that they have drawn on the example 1 there to the right looks nothing like this. But this is really legitimately what the graph looks like. Why does theirs look different? That's right, because they numbered the axes different. You have to pay attention to that. Look, the y's are numbered by halves, and the x's are numbered by 2s. That's a 4 times difference. So pay attention when you're doing big ideas math and they ask you to choose a graph, for example, among some others. If they choose one that works, make sure you're paying attention to the numbering of the axes. Take a look, we have the point 4, 1, which we anticipated. When you put x equals 4 in here, take a fourth of it, you get 1, and the square root of that is 1. Okay, and notice that the next point that they have graphed belongs to the number 8. I don't like that one. Look at the 16, that's the next integer plottable y value. They go clear out there at 16, and they only go up to 2. That's what we anticipated. The numbering's different, so pay attention. Okay, the next one, part B, says to graph -3 cube roots of x. What transformations are we going to have of the parent on this?
Reflection and a vertical stretch.
Stretch.
Vertical stretch of 3. This is what the original looks like. So, can somebody with their fingers in the air tell me how this thing's going to be? Okay, thank you for that. It's going to go this way. It is. Can you draw the graph for me? Looking at me, can you draw the graph of that? How it's going to, what shape it's going to have? Nice. Did you do it? How do you do it? How's it going to graph? Good. That's good. I like that. Okay, you went backwards, but okay, that's still the same. No, it isn't the same one. Try again. Yeah. This, remember, don't forget about this part.
Yes.
That's what you're forgetting.
Oh, yeah, I see.
Yeah, it's going to go like that. And it's going to drop down faster because we're stretching it. So where this was a -1, -1, that point on that one right there will go down to what?
Or it would be a +3, right?
Go down to -3.
Yeah.
Oh yeah, +3. Yeah, you caught me on that. Okay. It's going to go back 1, and it's not, because it's reflected, it's not going to go down, it's going to go up. This one was down before, it's going to go up, but it's going to go up 3 times as far. So this is going to have a, when we draw it, it's going to drop hard right there, then down to that 3 and out. And the significant stretching, the observable stretching is going to happen right in here, because this is going to go back 1 and up 1, 2, 3 here, and then out like this. But it's going to drop hard right there, and then drop down to 3 when by the time we hit 1 here, and then come out. So the big drop is going to be observable right here.
After you go up 3 and plot that point, would
Yep.
you go, like the next one you went up, would you go up 6?
Nope. Nope, that. 1, 2, 3. This is going to be a point on it. This is going to be a point on it because 0 doesn't do anything. And this is going to be a point on it. And the next one that I could plot would be the cube root of 8, which is 2. Right? Times -3. So you were right. It is -6. If I go clear out to 8. So if I go out to 8, it's going to go up. Not down, not 2, but 3 times as far as 2. But it's going to go up because of the negative. 1, 2, 3, 4, 5, 6. And you were right, Rachel. And then over here, if I go out 8, 1, 2, 3, 4, 5, 6, 7, 8, I'm going to have to go down. Not 1, but 6. 1, 2. Not 2, but 6. Yeah, that was 2. Okay. 3, 4, 5, 6. Okay. So you can see it's gonna have the same shape. Well, I didn't draw that very well. But it's gonna be quite a bit wider and open differently. If you take a look at the graph that they've got in your book, notice that the axes here are numbered the same this time. Notice that both the y-axis and the x-axis are numbered by 1s. You see it? Yeah, you're looking? So this time it does look like it was, not distorted like the first one. You've got to pay attention to the way the axes are numbered. Yeah, you can definitely graph it on there and see. And by the way, folks, I think, I haven't tried it on these new graphers, but I'm pretty sure, because they've got the same things the other ones did, plus some other cool, wonderful things. I'm pretty sure that you can put a grid on this so that you can actually count on your screen if you want to get an accurate graph or see if it's correct. So if you go to y equals, if you go to y equals and put in, you can compare the two. Let's just put in the parent for this. It would be x raised to the parenthesis 1 divided by 3, and then -3x raised to the 1 divided by 3. Am I making any sense to you?
Yeah.
For those of you watching, that's what I'm talking about. Okay. And then if you graph both of those in the same standard screen, so a zoom standard, You see the nice flat parent, and the other one's quite a bit wider and coming down the other way. So that looks like what we expected, right? Now, if you want to actually be able to count and see, you know, if you're looking on big ideas or on a test or something, and you want to see, did I actually graph this one that I'm choosing? You can go second and the zoom key and format the screen with a grid. So go down to the fourth one, no. Go down to the third one and over to grid line and hit enter and then graph. And it puts a grid on there for you. They look like rectangles instead of squares, but that's because your screen is wider than it is tall. So it makes rectangles out of it. It's called an aspect ratio.
Can you say that again?
Say what again?
How you
Yep.
made it a grid?
You go to format, which is just it's the blue aspect just above the zoom key.
Oh,
So you go second format. You go down to the third line and go over to the third choice which says grid line on. Hit enter and graph. It gives you a grid where you can count. Okay. Y'all see it?
Yep.
Now listen, I don't want to get a bunch of calculators returned to me with a bunch of little graphite marks because you're touching this as you count. Do it carefully and don't mess up these screens. This is the weakest part of these calculators are these screens. Be nice to them. Okay? All right. So you can do that and you can count. And by the way, you can make those things that look like rectangles. You can make them look like squares if you want. I'm pretty sure there's a zoom square. Try that. Go to zoom. Come on. Zoom. Where is it?
Square.
Where? Is it way down at the bottom?
oh yeah.
Oh, I see it. Number 5. Yeah. Zoom square. And it will design your screen size to square things up so that you can count. That'll look right.
Nice.
Okay? So that's a zoom option too. Look at what your window did when you have that zoom option. It went from -16 to 16 and then -10 to 10. That takes care of the aspect ratio. It puts 32 marks here and 20 here, and that's the aspect ratio of the screen. You know what I'm saying? Yeah. You know what I mean by aspect ratio? Nearly all TVs that you buy today have a 9:16 aspect ratio, but this is a 2:3 almost. All right. Anyway, let's move on to example 2. It says, describe the transformation of f represented by g, then graph each function. When it says graph each function, it means graph the parent as well. And what you can do, put those things in your screen after you've identified the transformation. You put those things in your screen and copy off your screen. You can do that if you're doing it on paper, or you can do that if you're doing it on Big Ideas Math. So you're going to use your calculator, but first, and I think this is really good for your brain, and most of you are really good at it anyway, so let's do it in order. Don't cheat on me by looking at the picture first. Of course, the picture's sitting right in front of you. But the very first one talks about how does the parent, square root of x, transform to get the square root of x minus 3 plus 4.
Goes up 4.
Right 3.
It goes what?
Up 4, right 3.
Up 4 and right 3. Y'all recognize the right, even though it's -3?
Yeah.
Okay, and what that means, folks, is that when you move it, this is something to observe and know that's going to be kind of nice for you. This one comes out like this. This one's going to go up 4, right 3, and do the same thing. So in other words, it moved the vertex of this, is what we call that. We moved the vertex from 0, 0 to 3, 4. And then it looks exactly like it did before, but it starts here. Its vertex is 3, 4. Now your calculator sometimes won't. But let's try that. Let's graph the transform function there. So go to y equals, clear it. It's going to be the square root of x minus 3. Y'all know where your square root button is, right? I hope. X minus 3. Oops. Crap. Come on. Plus 4. Now, I want you to hit the trace key. And notice it starts at y or x equals 0, y equals nothing. Right, when you hit the trace key? Because it doesn't have anything until you get to x equals 3. So you're going to have to hit the right arrow button until the x's get up to 3. Then you'll start to see things. Now, I want you to go back until your cursor disappears. So go back and watch, then go slow, go carefully. Go back till your cursor disappears, and then go forward 1 until your cursor appears for the first time. Y'all did that? It appears to be at the vertex of this thing, right? But what does it tell you the vertex is? 3.17 and 4.41. You gotta know that isn't quite right. You gotta know that the vertex is actually 3.4. So your calculator can lie to you. And the reason why is because it's got these vertical pixelations in it, and it won't jump into the first one until it finds a single dot in that pixel row. Because these things, these graphs right here, if I'd drawn them right, if the parent graph actually starts right here and it has a vertical, it's straight vertical for just an instant before it starts to come out. I exaggerated that on purpose. And in the pixel row right here, if you had a pixel row and your calculator was trying to draw right here, it will not put a point in this row, this pixel row, until it moves right enough to where there's only one point in that pixel row. If there's more than one point that it could graph in this row, it won't do it because it perceives that as a non-function. So I don't know if you bought that explanation or not, or if you even care. The calculator will lie to you about the vertexes, is what I'm telling you. You got to know where they are from the transformation. All right, take a look at the B part. It says we're going to transform the cube root of x, and it's going to be the cube root of negative 8x. So let's do that transformation then. The cube root of negative 8x. So why don't you graph that? Well, wait a minute. What's the transformation? What is this transformation?
Horizontal shrink by a factor.
Horizontal shrink of 1/8 and
Reflection in the y.
reflect in the y. Do you all recognize that? If not, we need to discuss that. When the negative is on the inside, it's a y reflection. And when the number's on the inside, it's a horizontal, and it's the reciprocal of this. It says the reciprocal is 1/8, it's a shrink. 1/8 is less than 1.
So if it was 1/8 x, would it be a horizontal shrink?
Yep. All right, so go to y equals and see if what you decided the transformations would be actually work. So we're going to go, this is what you do. You type parenthesis, negative 8x, close it, raised to the parenthesis 1 divided by 3, because the whole thing is inside the 1/3. Graph that. Does it look like the yellow one here has been reflected over the y? And then shrunk? Yes. Yeah. It's now a little taller. It's actually resulting in a shrink. By the way, folks, since this was an 8, you can actually cube root that negative 8 and get a vertical stretch of 2. If you pull that out. And a reflection over the x. But isn't that the same thing when you're doing cubes? Isn't a reflection, take that yellow one, isn't a reflection over the y going to get you exactly the same thing as a reflection over the x? So pulling that negative out or leaving it in with a cube root makes no difference. The reflection over the x and the y is the same for that. Did you follow that? If you were to graph this graph and also graph this graph, they would be exactly the same. Because our rules for x, or for our rules for radicals says that you can cube root negative 8 and cube root x separately. That cube root is negative 2. See? They're the same. The transformations are listed differently. Look at this. This one written this way is a horizontal shrink of 1/8. And I expect you to follow the rules if that's inside. Horizontal shrink of 1/8, reflection in the y-axis. If you were going to simplify it and do this, then you better show me the simplification before you list the transformations, in which case you would say a reflection in the x and a vertical stretch of 2. But if you give me a reflection in the x and vertical stretch of 2 with only that written, I will not give you any credit. You got to show me that you transformed it to this before you listed the transformations. But they are the same. Okay, moving on. All right, example 3 is supposed to be a practical application. Let's see if we can at least do it. Maybe we don't believe it's practical, but we're going to try. It says the function e of d. I gotta clear this out so I've got a place to write. It'll still show up on this video. I'm gonna write it down up here. They've got these things written kind of weird. They've got a capital E of d. What it means is these variable the letters that they're using have got some meaning in this problem. So we're not using f of x or g of x. We're using e of d. And it says e of d is 0.25 root d. And they're going to explain what this means here in just a second. It says, the function e of d is 0.25 root d approximates the number of seconds that it takes a dropped object to fall d feet on Earth. So if you wanted to figure out how long an object would be in the air, like a stone or a ball bearing or something like that, something heavy and small, so the air friction doesn't come into it. If you wanted to know about how long it would take to drop it off a 300-foot building, you could put 300 in for D, square root it, take it times 0.25, it would give you the number of seconds it takes for it to fall. You understand what this thing tells you now? So D is the distance it's going to drop, and E of D is the time on Earth. That's what the E stands for, is Earth. It's going to do another planet now. The function M of D equals 1.6 times E of D approximates the number of seconds it takes to drop an object d feet on Mars, hence the capital M. We want to write a rule for M. And then, does it take a dropped object to fall 64 feet on Mars? So we're going to answer the question once we get a rule. But what we have up here for Mars is M of D, same, that still stands for distance, is what does it say? Or 3, what is it? 1.6 times E of D. Well, that's not a very hard thing to do. That's 1.6. Just replace E of D with 0.25 or a D. Well, what's 1.6 times 0.25? So there's your formula for Mars. It's just a quick substitution of what E of D is and then do the arithmetic. It's not a big deal. How far is it going to fall in 60? How long will it take to fall 64 feet on Mars? 0.4 times 8. Did you follow? Did you figure out where I got the 8 from?
No, where'd you get the 8?
Because it said 64 feet, and that's what D is. Square root of 64 is 8.
Okay.
Did y'all follow that? So 3.2 seconds. How long would it take it to fall on Earth? $64 feet. 2. Square root of 64 is 8. A fourth of 8 is 2. So it would take 2 seconds to fall 64 feet on Earth. It would take 3.2, so not even twice that, but 3.2 seconds on Mars. Because Mars is way less massive, so it has much less gravity. It also has much less air. But we didn't consider air friction in our calculations. Anybody ever see Total Recall? Arnold Schwarzenegger? He's on Mars. He has to run, they've got these pressurized places, and he has to run from one building to the next because there's no way, he's got to escape or they're going to kill him. And it's pretty good for the day and age that they made that to show the lack of air pressure. It's only about 1% of what it is on Earth, which means that you're pushing out at the same time the air pressure on Earth is pushing in on you, and so you can't feel it. Turbo pressure in your cells. You get in a place where that doesn't have any pressure. Depressurized, out in space or on Mars, and you explode, but you don't blow up like a bomb. All of your tissues just start to expand. Your veins get bigger. Your eyeballs start to come out. Your face gets thicker. It's just nasty and painful. Anyway, it was pretty good. Total Recall. I don't recommend it because it's rated R, but that particular scene is pretty well done.
He's not the teacher.
Did Tate or Bailey come in?
Did Tater Bailey? Nope.
Bailey would stay long.
I recognize it, but I don't recognize
All right. Anyway, that's neither here nor there. I just want to talk to you about air pressure for a second. All right. Let's look at example 4. It says, let the graph of G be a horizontal. Oh, now they're going to give us a bunch of stuff. Let the graph of G be a horizontal shrink by a factor of 1/6, followed by a translation 3 units to the left of the graph of f of x equals the cube root of x, and write a rule for G. Whew. That's a mouthful if you read it that fast. So in math, we typically go back and read and try to figure things out. First of all, the thing we're supposed to transform is the last thing that they list, almost. It's the cube root that we want to transform, not the square root. So f of x is our parent cube root. That's what we wish to transform in such a way that G will be, well, let's see. How many transformations are we doing? Are we doing more than one?
Yeah.
Horizontal shrink? Okay. Now, for those of you who have not had me in class before, if there's more than one transformation, especially if they're complex, this isn't necessarily really complex, but if you have more than one transformation and you want to show me your work properly, you do one transformation at a time. And our final thing is going to be G of x equals something. So in the middle, I'm going to use H. And I'm going to do the first transformation of f, And I'm gonna call it H, and then I'm gonna transform H with the second transformation and call it G. Do you understand what I'm doing? I'm only considering the first transformation first, and I'm calling it H. It's an intermediate step. Let the graph of G be a horizontal shrink by a factor of 1/6. That's what I want to do. How do I do a horizontal shrink by a factor of 1/6? 6 inside. That make sense? Because we have to reciprocate the 1/6. Okay, then it says, followed by a translation 3 units left. So what I want to do now is I'm going to do G of X, which is going to be H of X. How, am I going left how far?
3.
Plus 3 then. Do you see that little intermediate step that I'm doing it for H in general? Because if you don't, a lot of people don't know how to handle that 6 and that X and all that stuff together. They don't know how to handle that. So G of X is going to be whatever my first transformation was, which was 6. My first transformation is going to be transformed 3 units left. And what that tells me, if I do this in a general way, is that my final answer is going to replace the X's in H with X plus 3. Like that. The X's in H become X plus 3. Whatever's in the parentheses here replaces the X's. Do you see that? And you could leave it like that for full credit for me. I don't know if Big Ideas will take it that way. Because what they really want you to do is to distribute. If you try to do this part to this without this step, you will likely mess it up. Because if you do this intermediate step right here, it reminds you that all x's get replaced with what's in this. And the reason why the x plus 3 is inside the parentheses is because it's a left-right transformation. It's inside the function. Left-right. Horizontal. Inside. When this indicates, the parentheses indicate to replace the x's with x plus 3, and then you can get it done right. It's when you do horizontal things, it's hard. And you got to pay attention and go really slow. And then it says, write a rule for G. We did. We didn't necessarily say to graph it, but if you wanted to graph it to verify that all of these things happened, you could. It's a horizontal shrink of a 6. So whatever that looks like, that yellow one right there, somebody went like this. Smashed it like that, and then they went and moved it over 3. So you should be able to verify that in your calculator. Okay. There's no questions. I'm moving on. Are you okay? All right, here we go. Example 5 says, use a graphing calculator to graph 1/2 y squared equals x. Identify the vertex and the direction that the parabola opens. Okay, that's a daunting task until you've seen it done. When you see it, or maybe you already know how, but when you see it, it's not going to be that bad. But you cannot graph it in this function or in this calculator unless you have some y equals. So I have 1/2 y squared. Equals x. And you cannot put this in this calculator by typing in 1/2 x squared. That won't do it. You have to solve for y. First step, multiply both sides by 2. That gets rid of the half, right? And then square root. So you get y equals the square root of 2x. But there is a plus or minus there because there was no radical to begin with. We introduced the radical. We weren't attempting to solve y for y, and when you square root in the process of solving, you have to have a plus or minus on it. Yes.
Can't we just turn our paper and make x like our y's because it's equal to x?
You could, except for it's not like this. When you graph something, it doesn't fall down like that. It falls down like that. It's not quite the same. It will be in this one because it's symmetric about the y, so it'll be symmetric about the x. It's not the case with all things like this one right here. If you just rotate that thing, you're going to have this branch on the wrong side. It goes up like that. So yeah, it's not just a drop to the x-axis. Okay. So in the process of solving, if you have to square root, you put a plus or minus on it. So what I really have is y1 equals root 2x and y2 equals negative root 2x. If you do it that way, your calculator will graph them because it perceives both of these as functions and it's right. You get the two together and you get a non-function. You get the bottom half along with the top half. I'm going to erase that. Just look in your calculators. You got to do both of those things. So the instructions were, use a graphing calculator to graph 1/2 y squared equals x. Identify the vertex and the direction that the parabola opens. So we're actually gonna graph it in two pieces, those two pieces. So we're gonna go in y1, the square root of 2x, and negative, and then square root of 2x. And graph that. And you get a blue one on top and a red one on the bottom, at least I do. Is that what you're getting, blue and red? Okay. And so we would graph that and follow, what you can do if you want, is you can go to the table. You have to go to table set. You can get some points if you want to plot. I'm gonna go 0 and increment by 1s. If you go to the table and you set it up right, you can get the blue y values and the red y values, and you can plot the whole numbered values so that you have something to connect when you graph. Because it's not just gonna be root x and negative root x, it's negative. It's got some transformations inside. So the points aren't gonna be exactly like the parent. You all know how to run your table? So you can get it like this. I know you guys didn't follow that very well, but you can get a table of values to plot if you want. Go back to the graph, and you can count out some nice crossings too, because you've got that grid on there. Okay? So it said to graph it, identify the vertex and the direction that the parabola opens. The vertex is at 0, 0, and it opens to the right. You okay? Last thing, graphing circles. Anybody remember the standard form for the equation of a circle? You learned this in geometry, or you were supposed to.
I did.
X squared plus y squared equals r squared.
Nope, that doesn't sound familiar at all.
Oh, I don't remember graphing circles. I remember like doing stuff with circles, but they were never like graph.
Right. You did things like inscribed angles or half the intercepted arc, stuff like that.
Yeah.
Do you want a brief explanation as to why that thing looks like the Pythagorean theorem? What in the heck does right triangle trigger? What does right triangles have to do with circles? And the answer is everything. Let me show you, just really briefly. If you don't follow this, it's not important for doing the exercise, but I just want to show you briefly why that's the equation of a circle centered at the origin. Let's say that I had a radius of 5 so you can see something. 1, 2, 3, 4, 5. The only reason I'm counting these out on the axes is so I have something to shoot for when I draw my circle. And I would draw it with a compass, except for my compass has got a pen attached. I don't want to use that on this. So it's going to be kind of a not the best circle in the world if it's free-handed. That look okay? So that's a radius, that's a circle centered at the origin with a radius of 5. And I want you to notice something. One of the points on there is this one right here. And look what it does. How far is it from here to here? 5. It has to be. All radiuses are the same length. They're all 5, right? If I continue this and make a right triangle out of it, I see that I would have to go out 4 and up 3 to get to that particular point on the circle. That's 4 and 3. And that's 16 and 9. Added together is 25. The square root is 5. Right?
Yeah.
Okay. I could also do one down here if I wanted to choose this one. I could go out 3 and down 4. And this would have to be 5. This is 3 and 4. And sure enough, that's a point on the circle. And you're going, yeah, that's great with 3, 4s, and 5s, but that's not all. If I took any point on this circle, something really weird and strange like this one right there, any point at all, that point would be such that this x value going out to there and the y value dropping down to it would fit the Pythagorean theorem and make that 5. However far out that is, that's a little bit more than 4, and it goes down not quite 3. A little bit more than 4, and then not quite 3. If I squared that actual distance and squared that distance and added it together, I would get 25 every time. And the set of points that has that condition linked together makes that circle. If you didn't follow that entirely, it's okay. The particular one that we were just looking at has a radius of 5, so we would put a 25 here. That's a circle centered at the origin with a radius of 25. Now, it's got an x squared and a y squared on it. So look at example 6. It says, use a graphing calculator to graph x squared plus y squared equals 16. So I'm just going to change this to a 16. What will the radius of it be?
4.
How are we going to get the calculator to graph it? Like this. Got to solve for y. Follow that little move? Then you got a square root. And it's plus or minus, because that will give you the top and the bottom half of the circle. And both the top and the bottom half by themselves are functions. So your calculator will graph them if you do it separate. 16 minus x squared. And we got to put those two things in y1 and y2. And there's something about your calculator we need to explain once you get it done. So get it graphed. Square root 16 minus x squared. Close it. Now, when you do the negative one, you can type it again, but for those of you that really want to know how these calculators function, you remember that you can find a list of y's in your vars key?
Oh, yeah.
So to do this, you could type in this. You could type y1 equals the square root of 16 minus x squared, and then you can do in y2 negative y1 without having to retype it. But you got to go find it in your vars key. That's what I'm going to do. You don't have to do it this way. You can type negative square root 16 minus x squared. That's fine. I'm going to do it this way. I'm going to go negative and then vars, y vars function, y1, and it will do the negative of what I had in y1. And here's what you get. And to remind you of primary, frowny face and smiley face.
Oh, you
That's
got
because you went back to a
square
standard screen.
there.
It looks like a football because it'll stretch it wide because of the aspect ratio. I left mine on square. Go to square screen, zoom square, it will clean up that aspect ratio and make it look like a circle, but there's gaps at the sides. It has to do with that pixel problem again, because as a circle comes down and comes down closer and closer and closer to that horizontal diameter, it gets steeper and steeper and steeper, and the calculator perceives that steepness where it has to put more than one point in a pixel row or column. It perceives that as a non-function and stops. But that is a circle. And the circle is radius 4 if you count it. Y'all see it? So the instruction was graph x squared plus y squared equals 16. Identify the radius and the intercepts. Intercepts means where it hits the x-axis. It hits the x-axis at 4 and negative 4, and it hits the y-axis at 4 and negative 4, and it has a radius of 4. Yeah. Okay, a lot of 4s there. Guys think you can handle it? Because that's it. We're done. If you can remember how to do this, you have to solve for y, and it gives you two pieces. When you do a parabola or a circle, it gives you two pieces that you have to graph.
What is did we talk about domain and range?
We better talk about domain and range for just a minute. We did talk about range or domain just a little bit. All right, so these are the three things. Pay attention here, folks, for just a second. The standard for square roots is that, and the domain of this function is x's, which are greater than or equal to 0, and the range is y's that are greater than or equal to 0. Because it's all in the first quadrant. There's nothing out here. We can't go left, we can't go down and get anything on this graph. Does that make sense to you? Yep. Domain is x's, which work. They're to the right. Range is y's, which work. They are up. Now, if you have a transformation of that that's out here, and let's say that this is 3 and this is 4, like we saw before, then the domain of that is x greater than or equal to 3. And the range is y greater than or equal to 4. It's all about the vertex. This guy right here, I don't care what the transformation is, makes absolutely no difference. It has a domain and range of all real numbers all the time. You'll hit every single x with a y, and you'll hit every single y. Well, and I have an x value. So I don't care what you do to that thing. Reflect it, move it, shrink it, stretch it. I don't care what you do to that. It will cover all the x's and all the y's eventually. Okay, so this one's all real numbers no matter what. For circles, I think you're only going to be dealing with ones at the origin here. I mean, we centered at the origin. So whatever this is, whatever r is, the domain is from negative r to r, isn't it? Negative r to r. No other x's show up. The range of this is also negative r to r, because it goes top to bottom, the same radius, and that's all you see. Nothing else goes beyond the radius. Okay? You all right with that? That's what domain, that's your discussion of domain and range. Does that help, Rachel? Yeah. Okay. All right. Well, I managed just to get it all done. Oh, I'm sorry. I'll shine this over there so you can see. Ew, gross. That's really bad. I don't know if you can see that, but there's your domain and range. Might want to open your screen up a bit. All right. Have a good day. Bye. That was fun.